the Central Limit Theorem, one of the most powerful ideas in all of statistics. Let's start with a population of adult male body weights. The population has a mean of 173 pounds and a standard deviation of 30 pounds. But notice, this distribution is not normal. It has a positive skew with a long tail stretching to the right. The question is, what happens when we take sample means from this population? Watch what happens as we increase the sample size. With n equals 2, the sampling distribution is still wide and a bit irregular. At n equals 5, it starts to narrow and look more symmetric. At n equals 10, it's clearly becoming bell-shaped. And at n equals 30, it's essentially a perfect normal distribution, tightly clustered around the true mean. This is the Central Limit Theorem. Regardless of the original population shape, the distribution of sample means approaches a normal distribution as the sample size increases. Let's state this more precisely. For a random sample of size n from a population with mean mu and standard deviation sigma, the sampling distribution of x bar approaches a normal distribution as n increases. In notation, x bar is approximately distributed as normal with mean mu and standard deviation sigma over square root of n. The conditions are straightforward. Either the population itself is normal, or the sample size is large enough, typically 25 to 30. And the samples must be independent, drawn as simple random samples. Let's apply this with a real example. Wechsler adult intelligence scores follow a normal distribution with mean 100 and standard deviation 15. If we take a simple random sample of n equals 10, the standard error is sigma over square root of n, which is 15 over the square root of 10, giving us 4.7. So the sampling distribution of x bar is normal with mean 100 and standard error 4.7. Using the 68% rule, about 68% of sample means will fall between 95.3 and 104.7. To summarize, the Central Limit Theorem tells us that the distribution of sample means approaches normal as the sample size grows. This works even for non-normal populations. Larger samples produce narrower, more normal sampling distributions. And this is what makes inference about population means possible.